Now let's consider a second design where we're going to choose a different zero, a different pole for our controller, and we're going to also have a different gain involved. So the first equation is still the same. The pole and the zero we choose for the controller, that angle still has to equal negative 45 degrees based on the previous steps, so that G prime, the angle of G prime, was 180 degrees. So I'm going to choose a different zero, again just arbitrarily choosing a zero of 3. So I can put that 3 in for ZC. Now that second term I can find numerically using angle or using arctan 2 in MATLAB. So that comes out to the not as round number, a negative 63.4 degree angle. Right, I can add the 63.4 to both sides. I can multiply through by negative 1, so the negative drops off of my angle term. So that means that that angle with the pole has to equal negative 18.4 degrees. Again, restating what the angle is, it's just the arctangent of the imaginary part over the real part, and that has to equal negative 18.4 degrees. Take the tangent to both sides, and that tells me that the pole has to be 8. So there was a little bit of rounding here, but if I pick a zero of 3, I need a pole of 8 then, so that the sum of these angles is the negative 45 degrees. With the zero chosen arbitrarily and then the pole chosen so that this equals negative 45, I can form my G prime for this set of zero and pole. So now I have an S plus 3 over S plus 8, S plus 2. And again here I'm going to leave it in factored form just so I can see where the poles are. But when I go into MATLAB, I will need to put it into my full form with descending powers of S. So let's see what the root locus for this chosen system of zero and pole is going to look like. Going into MATLAB, I'm now on design 2. So we're going to set our 0 to 3 and our pole to 8 and create the root locus based on this. We see the root locus certainly has a different shape, although again by design, the desired closed loop poles are still going to lie on this root locus. Okay, so dragging it around, we find here to get to the negative 2 plus or minus 2j, this requires a gain of 16. Now the gain is higher, it's 16 this time than it was in the design number 1, but for these more complicated controllers, a higher gain does not necessarily always correlate with a higher input effort needed, because it's going to depend on the gain we put into the system and the zeros and poles that we choose. So through the simulation, we'll see what the actual input effort is. But this gain combined with the zero and the pole that we just found, that's going to form our closed loop system. And if we see the predictions here, it predicts the same overshoot, 4.32% we actually saw in the previous one, because that's how the baseline second order system should behave. In theory, our peak time should be the same, but again, we'll see through simulation what it actually turns out to be. If we put together our controller and our gain that we find that this has a closed loop transfer function. I have this in the factored form so we can see how it's going to behave. So we have the dominant poles exactly where we want them, minus 2 plus or minus 2j. But compared to a baseline system with just those two dominant poles, we have a third pole at negative 6, and we have a 0 at negative 3. So the extra pole and the extra 0 are within 4 times the real part of our dominant poles, so they're certainly going to have an effect, and they're not necessarily close to each other, the negative 3 and the negative 6. So we'll see in simulation, where does this pull the response of our system? Simulink is identical, but my Z1, P1, and K are now different because I have a different design. So let's see what this does in simulation. All right, so I can see the output of the system. I can see the input. The input actually does go up to 80 this time. So the maximum effort is higher than it was before. It is twice as high, and the gain is twice as high. But again, they don't necessarily always agree with each other. So the fundamentals of the controller, it does work. It drives our error to 0 at steady state, and therefore it drives our output to 5 volts, which is exactly what we need to have happen as the primary goal of our controller. Does it stabilize the system? Now, how does it do it? We see, it's easier to see from the MATLAB computation here. We have a max overshoot of 8.24%, and we have a peak time of 1.25 seconds. So compared to design 1 and to the baseline, which actually they were the same, here we have a higher max overshoot and we have a lower peak time. And that's being caused by the actual system having that extra pole and that extra zero. And in this controller, we have a higher maximum input of 80 than we had compared to the first design. So we'll compare all three designs at the end for a true comparison of all the choices we made. But so far this controller, probably not as good as the first controller because the performance doesn't match what our desire was in terms of the overshoot and the peak time. Also requires more of this input effort to get where we need to go.